The process by which bones grow is called osteogenesis, and there are two types of osteogenesis: intramembranous, which we've looked at, and endochondral, which we'll look at now. Most long bones are formed by endochondral ossification, and in this process a small cartilaginous model of the bone is first constructed and then replaced by bone tissue. Early on in embryonic development, the mesenchyme in the region of the future bone differentiates into hyaline cartilage, which is covered by a perichondrium. As the bone grows, both interstitially and appositionally on its surface, the shape of a long bone can be seen. With growth of this cartilaginous model, the perichondrium is invaded by capillaries, triggering the transformation of the perichondrium into a periosteum, and the innermost cells of this periosteum specialize now as osteoblasts and lay down a bone collar around the middle of the shaft. This bone collar interferes with the diffusion of nutrients into the cartilage, and chondrocytes in the center of the shaft, called the diaphysis, start to swell up and soon disintegrate and die. Simultaneously, the matrix surrounding these dying cells begins to calcify. Small blood vessels now penetrate the bone collar through holes bored by osteoclasts and invade the area of calcified cartilage within the shaft. Osteoprogenitor cells, which are carried in with the blood, differentiate into osteoblasts and start to lay down bone on these spicules of calcified cartilage. In this manner, what was cartilage becomes a primary ossification center, built of spongy bone and constructed on a framework of calcified cartilage matrix. As soon as this bone is laid down on these spicules of calcified cartilage, it begins to be resorbed by the action of osteoclasts, which were also carried in by these blood vessels, resulting in the formation of a marrow cavity. And this process continues in both directions, resulting in the formation of a marrow cavity filling the diaphysis of the bone with only a few of the original trabeculae remaining. At the same time, the bone collar becomes thickened by appositional growth on its surface and widened by resorption of bone on the inner surface. And we'll look at this in a bit more detail a bit later. At this point, the head or epiphysis of the ends of the bone on both sides is still composed of cartilage, while the shaft consists of a collar of bone around the marrow cavity. In the later stages of embryonic development, a similar process that we've just seen takes place in the epiphyses at each end of the bone, although not necessarily simultaneously, forming what comes to be a secondary ossification center. However, no bone collar forms on the surface of the cartilage, as this is specialized as articular cartilage. The function of these secondary ossification centers is to allow the ends of the bone to expand radially in this direction here rather than longitudinally. So the surface of the joint retains its size relative to the increase in size of the bone and to the individual. By now, all that remains of the original cartilaginous model is the articular cartilage covering the epiphyses at each end of the long bone, and two strips of cartilage, shown here, the epiphyseal plates, at the junction between the diaphysis and the epiphysis. Articular cartilage here and here plays no further role in the growth of the bone. The epiphyseal plates here and here are solely responsible for the subsequent increase in length of the bone. Increase in width of the bone is achieved by apposition of bone on the surface under the periosteum and removal of bone on the inner endosteosurface, so that this compact bone here doesn't become too thick and the size of the marrow cavity can increase. Growth in length of the bones, and therefore growth in size or height of the individual, is determined by the activity of the cartilage cells living in these epiphyseal plates, and it is here that growth hormone, somatotropin, coming from the pituitary gland, exerts an important effect. Too little growth hormone and dwarfism results, too much growth hormone and gigantism results. Eventually these epiphyseal plates disappear, and after that happens, no further growth in the length of the bone will occur. Growth in the length of the long bones depends upon the presence of cartilage in these epiphyseal plates and its conversion into bone. A number of distinct zones can be observed in the growth plates, in the epiphyseal growth plates, and changes in the cartilaginous cells in these epiphyseal growth plates result in the formation of bone spicules, which will eventually fill much of the marrow cavity and increase in the length of the bone. The first area called the zone of resting cartilage, and this area here provides the chondrocytes that will allow for lengthening of the bone. Chondrocytes at the interface between the zone of resting cartilage and this zone of proliferating cartilage start to divide and become organized into these columns of cells. Division of chondrocytes in this zone is responsible for lengthening of the bone. As bone is added at the metaphysis, that's this area down here, pushing it away from and thus lengthening the diaphysis. This process, this division, is stimulated by growth hormone. These chondrocytes, still arrayed in columns, greatly increase in size and start to accumulate glycogen. This red deposit here is glycogen, which is showed up by this staining method. And they secrete vascular endothelial growth factor, VEGF, which attracts blood vessels into this area. They, of course, actively, as do the cells higher up, secrete matrix. In the zone of calcified cartilage, the chondrocytes stop secreting any matrix and other proteoglycans and begin secreting alkaline phosphatase, which, as you remember, is an enzyme that is essential for mineral deposition, and calcification of the matrix between these chondrocytes occurs, and this then cuts off nutrition to the chondrocytes, which begin to degenerate. Finally, in the zone of ossification, or zone of resorption as it's sometimes called, the calcified cartilage surrounding the degenerating chondrocytes is digested by osteoclasts that move into this area from small blood vessels, and as they digest the calcified cartilage, they leave spicules of calcified cartilage, shown here in blue. The blood vessels that have invaded this area bring in osteoprogenitor cells, which differentiate into osteoblasts, and using these spicules of calcified cartilage, they begin to secrete osteoid, which, as you know, will be mineralized and transformed into bone. These spicules of calcified cartilage with woven bone on top of them will be digested away by osteoclasts and replaced by spongy bone through the action of more osteoblasts, so that eventually we end up with spongy bone in this area. At the same time that growth is occurring on the diaphyseal side of the growth plate, the same process is also occurring on the epiphyseal side of the growth plate. Eventually, the reserve cartilage in the epiphyseal growth plate is all used up, and all of the cartilage is replaced by bone. At this point, the epiphysis and the diaphysis become continuous in a network of spongy bone, and any increase in length of the bone ceases, and this is at about age 20 or around there. At the same time that bones are growing longer, they're also growing wider, as new bone is laid down appositionally underneath the periosteum here, and as this compact bone covering the diaphysis becomes thicker, its width is maintained by the removal of compact bone on the inner surface of the diaphysis by osteoclasts. And of course, there has to be constant remodeling at this area here, the metaphysis, in order to maintain the shape, the structure of this long bone at both ends.